Successful commutation occurs when, at the point of commutation or the neutral axis, the armature coil is shorted by the brush, the current carried by the path is equal, and there's no EMF induced into the coil. And for this to happen, the flux must be symmetrical. The current flowing in an armature coil changes direction as its bar contacts passes under the brush. The point at which no current flows in the coil is when the brush is centered in the coil. This is also the point that no counter EMF is generated. This is necessary for commutation to be successful and to experience no arcing at the brush. This illustrates what happens when a coil is under commutation. Current decreases until it is zero at the point of the coil is centered at the brush, then reverses direction. The brushes used in industrial motors are graphite and electrographite materials. These materials are good conductors, however, they do present some resistance to current flow due to their resistive nature, and this is a good thing. Resistive brushes aid in the process of commutation. As soon as the brush contacts the segment, some current will start to flow from the segment to the brush. How much of the total current flowing depends on how much area the brush is contacting. As the contact area between the brush and the commutator segment increases, the resistance to current flow decreases. Current flow from the segment through the brush increases as the brush contacts more segment. Now, when the resistance from each circuit to the brush is equal, there's no current flowing in the coil under commutation. It is at that point that the brush is shorted out, the coil. As the contact area between the brush and the commutator segment decreases, the resistance to the current flow increases. Current flowing through the segment decreases as the brush contacts less segment area. As seen here, contact resistance has the tendency to force the current in the short circuit coils to reverse. The brush is in the center of the coil pitch. This is due to the offset construction of the coil. And you can see that in this picture. The coil sides span out, and the center of the span is where the coil is connecting to the commutator. Again, you can see the offset in the construction of the coil. During commutation, the coil sides are centered between field poles and the coil connections are centered at the brush. As the coil rotates clockwise, it goes under commutation where the current in the coil reverses. At the point of commutation, there is no current flowing in the coil from either side, and there's no EMF induced into the coil. If there is sparking at the brushes, it can mean the commutation process is not occurring properly. It's possible, not always what might be happening, but it is possible. Improper neutral setting, faulty electrical coils or connections, improper shimming dissymmetry between armature and field poles or interpoles, over or under commutation, interpole strength is too high or too low. Magnetic fasteners installed in interpoles, we know that would change the strength of the interpoles. It could also be caused by improper mechanical adjustments like pole spacing or brush arm spacing. There's just a lot of things that can go wrong, and typically when we're looking at arcing, we have to eliminate what it's not.